and the beginnings of the mole. Who remembers their, early atom scientists all together? We had John Dalton was first. He did some amazing stuff with the atom. He basically is the creator of what we consider to be an atom. His original model of atoms were these spherical billiard ball style atoms that basically combined, and that was its smallest divisible piece was an atom. So all of hydrogen are like little balls, all of nitrogen's a little ball, all of chlorine or iron or any of the elements on our table, they were just balls that stick to each other. No mention of electrons, no mention of protons, none of that was discovered at this time, because it's like a billion years ago, 1807. So he started combining these gases and seeing how they balanced. So he was measuring their weights. So by masses first. So the first way they were combining them is he was looking at these reactions of hydrogen and oxygen gas. So the hydrogen-oxygen gas goes together. It makes water. It's very exciting. But it took 11.1 grams of hydrogen gas and 88.0 grams of oxygen gas. But nitrogen gas needed 46.7 grams and 53 grams of oxygen gas to make NO2. To short a very long, complicated series of events that happened over a very long series of time, there were no patterns in mass. So there's no patterns whatsoever here. So there was no way of predicting how much mass of something would react with the mass of something else. You could measure them, create tables, but there was no predictive patterns in the atomic theory. Next guy, Joseph Gay-Lussac. It's French, so I'm going to say that wrong for sure. He started calculating things by volume. So he was looking at specifically gases and how they work together, but he was going to measure how much gas there was. So we're going to take a look at this. And so he had 1 liter of H2O reacts with 1 liter of chlorine gas to get 2 liters of hydrochloride gas. It's basically that gas that you can react with water to make hydrochloric acid, but as a gas it's called hydrogen chloride, not called hydrochloric acid. And we can see how much you guys remember from Science 10. Let's do a little bit of writing here. We're going to put H2 plus Cl2 makes HCl. So that's a, a reaction. What do I need to do to balance this reaction? You guys remember how to balance chemical reactions, right? See lots of worried looks out there. Yes, we do need to learn how to balance reactions. What do I need to balance this reaction? This one's a kind of easy one. Is it balanced the way it is? No. What am I short of? One of the things isn't big enough. I got 2 hydrogens and 2 chlorines makes 1 hydrogen and 1 chlorine. That's bad. I need 2 of those. Does that work for everything now? Is this now balanced? Not hearing a lot of confirmation. It is all balanced. It's a shortcut here. So we're going to put 1s there to balance it out, showing me I'm all finished. So this is our balanced chemical reaction. We have a hydrogen gas, which is an H2, plus a chlorine gas, that's a Cl2, makes 2 sets of hydrogen chloride. Okay, that's good news. Let's do the other reaction. I'm going to do that with the slightly other color. We're going to put N2 gas plus H2 gas makes an ammonia gas. How does this lovely thing get balanced? Do I have enough nitrogen? on the right side? No. So I'm going to need more nitrogen. That's important. So nitrogen's good. How many hydrogens do I have on the right now? I have 6 hydrogens over here, right? I have 2 sets of 3, which makes 6. How many of these do I need? 3 of these. So, back to pen, put 3 here and 1 there, and we're finished. So now I've balanced both of these reactions. What am I noticing with my liters and my reactions? So what was noticed here by Joe here, we have these whole number ratios were matched here. The whole number ratios matched, which is very easy to predict. So if I got 1 liter here, that's 1 here. And then the 1 liter here, 1 liter here, 2 liters here, match that 2 over here. So the amount of liters, the volume of these gases, matched with the coefficients on top of their chemical formulas. So as we were balancing them, these matched. So let's see if I can draw this in here like this. Put that there. I think that's there. So if I do this like that, these all line up this way. So hopefully that makes sense, and hopefully you can see that on the screen, how the numbers in front of balanced reactions actually corresponds to the volume of these particular gases when they're under reaction. That's the main part we did here. Okay, so Avogadro, very important dude, he said equal volumes of different gases will have the same number of molecules. In other words, so if there's the same like size of a certain gas, that gas will have the same number of pieces in it. Now this works because gases are very far apart. So the volume of a gas is very directly proportional to how many things are in that gas. All the little pieces of that gas that add up to the volume of the gas is directly proportional to that volume. So we're going to take this second reaction that we had, and we're going to put that into our lovely containers that I have drawn for us here. So slide this up a bit. So the first one is going to be N2. This gas is full of N2. This tank will be full of H2. And this tank will be full of NH3. So based on my particular drawing of this, I don't think I used a scale. I was just winging it. But you can see small, big, and medium in this case. There is 1 liter of nitrogen. And there are 3 liters of hydrogen. We put these 2 gases together, and we get 2 liters of ammonia gas. And basically, we can do this comparison. So let's say, for our lovely sake of argument, that I'm going to put, let's assume that there are actually just 3 molecules of nitrogen gas, because I don't want to draw too many. So those are 3 little sets of N2, right? That's all that we're doing there. I just picked 3 because why not? How many, so that's a total of, I just want to write this here, 6 atoms of N. So there are 6 total. 6 N's altogether. How many more hydrogens should there be? Based on this particular tank. So if there's 3 liters of hydrogen gas, how many molecules of hydrogen should there be? Well, 18 atoms. Because it's 3 times more. Because there's 3 times the volume, so there's 3 times as many molecules. So I'm going to draw 9 sets, so that's 18. So I'm going to draw 9 little sets of hydrogen. I'm going to draw them very randomly. Because that's totally how gases work. So that is, switch colors, oops, leaning on the sides here a lot, 18 atoms of H. So when we're in a chemical reaction, we've learned in grade 9 and grade 10 and grade 8 and forever that we can't make or destroy atoms. They don't work like that in chemical reactions. We can shake them up. But so I know before anything else, I know I'm going to have 18 atoms of H. Oops. And I know I'm going to have 6 atoms of nitrogen. So that's I know for sure. How many NH3s are there going to be? How many ammonia molecules should there be? Because I know I can't break any of them. I can't take them and make them not exist. 6 sets. So I'm going to have 6 sets of this. 1, 2, 3, 4, 5, 6. And I'm going to draw my little sets like this. I think this looks okay. All right, I think that looks good enough. So that count still works, right? I still have 18 blue ones and 6 purple ones. And so that's 2 liters of ammonia gas. So all of these things are matching. So this is how these gases are related to each other. This is how these react to each other. This is how their proportions are. So our definition is now what is a mole. So a mole is a really interesting way of saying it, but specifically the best way to describe a mole is a counting set. A mole is a certain number of things. Kind of like things like dozens, pairs, anything else that you count sets of. So when you say I got 3 dozen, I know that's 3 times 12, and I can count the total numbers of those. And so a mole is just basically a fancy molecule version of a dozen. And so that fancy molecule version of a dozen is based on our carbon atom, because carbon is our basis of life, and how much organic chemistry we love. And so we're going to say that carbon is exactly 12. So carbon being exactly 12, we're going to have, that's how many particles there are of little atoms. Now, the good news is that 1 mole is equal to a very awesome number. Molecules are very small, right? Really, really small. So in like 12 grams of carbon, you would expect to see a lot of them. So this is going to be a really big number, and we're going to get all of our scientific notation out with this lovely thing. It is 6.022 times 10 to the 23. So this is our number of particles in a mole. So this is the number of things in the set. Now the reason we write it in our scientific notation, because I don't want to write 20 zeros. That's a lot of zeros, right? It's 6.022 20 zeros. It's a huge number because, say, 12 grams of carbon. 12 grams of carbon, you could have like a handful of carbon that would be 12 grams. And it would have this many particles in it, which is a lot. So 1 mole is 6.022 times 10 to the 23 things. That is our number, like a dozen is 12, or like a pair is 2, or any other combination set that comes in sets of things. Does that kind of make any sense? Using this particular value, we're going to define something called an AMU, or an atomic mass unit. So it's defined as 1/12, which is a great number, 12th of the mass of 12 carbon. Or, in our accuracy, 1.66 times 10 to the minus 27 kilograms. So that is equal to 1 piece of a nucleus. So every atomic mass unit weighs 1.66 times 10 to the negative 27th kilogram, which is another one of those numbers you won't use a lot of. It's true, but one, say, proton weighs about this much. 1 neutron weighs about this much. Does an electron weigh this much? No, electrons are way smaller. So, that was a little bit of a trick question. So, no, protons and neutrons, the things in the nucleus, weigh this much. And when we're weighing our compounds, our chemicals, we weigh nucleuses because they actually weigh something. An electron is 10,000 times smaller than a proton, and so electrons essentially weigh nothing when we're counting them all up. Even if I added up all of your electrons, they would be 1/10,000th of your weight, which is beyond most of our significant digits measurements. So, we will now be starting to refer to our lovely periodic table. We're actually going to get into some masses and some numbers. The calculators are coming back today. No more naming. We're going to get into the calculator stuff. This part's good. So we're going to look on our lovely periodic table for these elements. It's easy for the first few, but we're going to look up the other ones. So as you guys are getting them out, you probably can look and see that 12 carbon weighs 12. Very exciting, right? It's exactly 12. If you look at your periodic table, does carbon say exactly 12? No. Why doesn't carbon say exactly 12 if the mass of a carbon-12 atom is exactly 12? Why isn't the periodic table telling me it's exactly 12? Does anyone know the reason why all those decimals exist in the periodic table? Our Science 10 told us that isotopes were elements that had different numbers of neutrons, so they didn't change the nature of what the element is, it just changed how heavy that particular element was. Because neutrons don't do anything chemically to an atom, they just change how heavy it is, and that's it. It has other properties, but it doesn't change it chemically. Like carbon-12 and carbon-13, you would not. They are chemically the same. So we're going to have, this is the atomic mass. This is the atomic number. What does the atomic number of an element measure? What's it counting in that atom? How many what? It's not the number of electrons. It is protons. Now, in the defense, electrons is often the same as the protons, unless it has an ion charge, and then your electron count is different. But the atomic number is defined as the number of protons. It often gives you a hint at how many electrons it has, but it's defined as proton number. So, what's the mass of a carbon-13 atom? Any guesses? 13 is correct. 13.00. Very exciting. I'm going to look. Is there a table on this side? Aha. Well, it's the same. Oh. Okay, sure. Anyways, that's not better. What about iron? What's iron's mass? Look at your table. What's iron? Anyone's allowed to say it. I heard it. 55.8. It's very quiet, but I heard it. What about oxygen? 16. We're going to call it just a single zero because that's the only one I know. Over there it is, it's actually 15.9994 on that table. So 16 is pretty good. All right, so that's the mass of each atom. Now, what we're going to use in all of our stuff is something called grams per mole. So we're going to measure a mole of them. Because measuring one particular atom doesn't make a lot of sense in chemistry. When we're doing chemical reactions, we never actually react one atom of anything with a one atom of anything else. We have entire groups and piles of them. So we're going to measure how many grams in 1 mole. Now, excellent news for us is they are the same numbers. The number of grams per 1 mole is the same number as how many atomic mass units one atom weighs. Those are the same numbers. So that's how we're doing these conversions, is that the grams per an entire mole of something is the same as the atomic mass units of the particular thing. Okay, so we can use the atomic masses from the periodic table to find something called a molar mass of a compound. So the molar mass is the mass of 1 mole of material. So, simply enough, normally we work with how many moles of something because that's something you can actually measure. We can have a beaker full of 2 or 3 moles of something. We can't get 1 hydrogen atom. It's not a thing for us. But we can have a mole of hydrogen atoms. We can have half a mole of carbon. We can have 3 moles of carbon. It basically allows us to do measurable things in the right sizes. So basically, molar mass is a addition of all the atoms. So I'm just going to write this here because it doesn't look like it's in my notes. I'm going to write this addition of all atoms. Learn how to spell. It's 1 T in atom. There we go. So addition of all the atoms in a compound. So when we look at a compound, we can figure out how much 1 mole of that compound weighs in grams by using the masses found on the periodic table. So we're going to break down this right here. So water, very easy. There are 2 hydrogens. And so we're going to multiply that. What's the weight of 1 hydrogen? How heavy is 1 hydrogen on your particular table, which I will use for all of our math? 1.0 grams per mole. What does an oxygen weigh? And there's 1 of them. It's 16, so 16.0 grams per mole. So what does 1 water equal? This math is kind of easy. Please don't use your calculator yet. It's water. It's 18.0 grams per mole. So another way of saying that is two hydrogens. 2 times 1 plus 16. So if you have 18 grams of water, you have exactly 1 mole of water molecules. You have exactly 6.022 times 10 to the 23 molecules of water. Does that make sense? A little bit? Okay, we're just going to focus on molar masses part today. So, carbon dioxide, very similar. We're going to do this as 1 carbon, which is 12.0, and 2 oxygens times 16.0. So that's 12 plus 32. So that's 44.0 grams per mole. So 1 mole of carbon dioxide weighs 44 grams. Does it kind of make some sense? We're just adding up all the pieces of an element. And so the next line is why we did the last week of work, because how much does 1 mole of aluminum oxide weigh? First, we need to know how many aluminums and how many oxygens there are. So we have to balance their charges like we did on the quiz yesterday. So aluminum oxide has a formula of Al2O3. And so we need 2 aluminum weights plus 3 oxygen weights. Masses. Keep saying weights. In chemistry class, weight and mass are the same. Sorry. Because Earth. So we're going to have 2 times aluminum plus 3 times oxygen. What's aluminum weigh? 27. 27.0, and oxygen is still 16.0. So we're going to put those 2 together, 2 27s and 3 16s. Now seems like a fine time to start using your calculator. 2 27s is 54, plus 3 16s is 48. So that's 102. 102 grams per mole. Yay. All right. Iron dichromate is a giant mess. Let's figure out what the formula for iron 3 dichromate is. So iron 3, that's a 3 plus. Dichromate is a 2 plus charge ion. No, it's 2 minus charge. Let me write that properly. It's a 2 minus charge ion, I'm pretty sure. Looking at dichromate is 2 minus. So I need 2 irons, Fe2 Cr2O7 3. So that's a very, very ugly compound. Let me just zoom this up here so you guys can see it on the screen up there. All right. So what's the total number of irons in this particular molecule? 2. 2 irons. So there are 2 irons. So that's 1 iron, looking back on the table, is 55.8. 55.8. And then we have, how many total number of chromium are there? There are 6 chromiums. 6 chromiums. There are 3 sets of 2. So that's 6 total chromiums. 1 chromium is 52. 8.0. And how many total oxygens do I have? 21 oxygens. And each oxygen is still 16.0. So sometimes it's useful to do like a whole second set. Say, okay, 2 irons, that's 111.6. And then 6 chromiums is 312.0. And 21 oxygens is 336. It's a lot. All right, add all those together, and we're going to get 1 iron 3 dichromate molecule, which is 759.6 grams per mole. So 1 iron 3 dichromate molecule. It's not really a molecule. It's a set of ionic compounds. Ionic compounds aren't molecules, but one piece is 759 grams in 1 mole. So 1 mole of iron 3 dichromate is 759.6 grams per mole. So this is the practice. It's several questions. You're just going to go through getting used to the table, multiplying, getting your calculators back in order. And every time we're doing these molar masses, they have units of grams per mole. So we're back to using our calculators, we're back to using significant digits, we're back to using units, scientific notation, all that stuff from the first unit. We're back into using all of those lovely things. We're kind of leaving the descriptive nature of the organic chemistry and the naming a little behind. Anyways, we have to use the names from the last chapter to get our formulas right, but otherwise we're kind of straightforward there.